Today we are going to learn about the topic of important properties of convolution, which is very important in the GATE examination. So it belongs to the subject of signal systems. Okay, it is there in the syllabus of electronics and communications, electrical and instrumentation. We know that a convolution is a very important operator. Now, convolution is a very important operator. Why do we generally use a convolution? The convolution is generally used to relate input and output in terms of linear time invariant systems. Okay, in the case of linear time invariant systems, in order to find the relation between the input and output, we use the operator of convolution. So when I have an LTI system, the input is going to be generally either x of t or x of n. If it is a continuous time signal, it is x of t, and the output is going to be y of n, y of t. Now, the output is represented as y of t is equal to x of t convolved with it of h of t. So, x of t is the input, y of t is the output, and h of t is an impulse response. What is an impulse response? Impulse response is very simple. If you have an LTA system, the response of the system when the input given as an impulse. When the input is an impulse, the response of the system is what we call as a impulse response. Now, why do we generally use an impulse response? Impulse response is one of the way of representing a particular system, because each and every characteristic of an LTA system can be represented using an impulse response. That is the reason why impulse response is a very important parameter, okay, for an LTA system. So that is something that you have to know about to understand the properties of convolution. What is an impulse response? So apart from that, to understand the convolution, you have to know the representation of a signal in terms of shifted impulses. Representation of a signal in terms of shifted impulses. Now, what is the meaning of a shifted impulse? Let us see that. Any signal, for example, if I consider a signal x of t, that can be represented as equal to integral of minus infinite to infinite x of tau del of t minus tau theta. And in the case of a discrete time signal, I can represent it as x of n is equal to sigma x of k into del of n minus k, where the value of k is going to be varying from minus infinite to infinite. So this is a way of representing a particular signal in terms of impulse. Now I'll tell you an example. I'll take an example so that you can be convinced that how can we write a particular signal in terms of a shifted impulse. Okay. So first of all, let us take an example. If I have a signal x of n, which is equal to something like minus 1, 2, 3, where the arrow is going to be at 2. In the case of a discrete time signal, an arrow is always going to indicate n is equal to 0. So here the n is equal to 0 is an arrow. Before that n is equal to minus 1, and after that is n is equal to 1. Now, if you observe here, if the signal only has 2 here, and there is no minus 1 and there is no 3, then this can be represented as an impulse. What I mean to say is that if I have something like 0, 2, 0, now this is a representation of an impulse, because unit impulse is generally given as 1 here and all the other times are equal to 0. So unit impulse is defined as del of n is equal to 1 for n equal to 0, and it is equal to 0 for n not equal to 0. Del of n is equal to 1 for n equal to 0, and it is equal to 0 for n not equal to 0 is how we are going to represent a discrete time unit impulse. So here, if I have something like this is nothing but 2 into del of. This is nothing but 2 into del of n. And similarly, if I have something like minus 1 comma 0 comma 0, minus 1 comma 0 comma 0, if you forget about this minus 1, if I have something like this, an arrow is present here and at minus 1 and this is equal to 0. So minus 1, 0, 0. Now this is nothing but it is a shifted impulse. Why it is a shifted impulse? Because if I have a signal like 1 comma 0 comma 0 where the arrow is present at 0, this is nothing but the shifted form of this particular unit impulse. Okay, a unit impulse is generally going to be 0, 1, 0 and so on, all zeros. The arrow is present here. That is a representation, right? So here del of n is equal to 1 for n equal to 0 and it is equal to 0 for n not equal to 0. Now if I shift it to the left side, which is nothing but the advancing of a signal. So when I shift the signal towards the left side, then that is nothing but 1, 0, 0. So when you are moving this side, one more 0 is going to come here. Now this is nothing but del of n plus 1. This is nothing but del of n plus 1. If this is del of n plus 1, then minus 1 comma 0 comma 0 is going to be minus of del of n plus 1. Minus 1 comma 0 comma 0 is going to be minus of del of n plus 1. So I am able to represent this 2, I am able to represent this minus 1, and similarly I can also represent this 3. So to represent this particular 3, I can write it as equal to the of 0 comma 0 comma 3 where arrow is present here. Now this is nothing but 3 into del of n minus 1. This is nothing but 3 into del of n minus. So 0 comma 2 comma 0 is nothing but 2 into del of n. So I can write it as 1. Minus 1 comma 0 comma 0, I can write it as 2, which is nothing but minus of del of n plus 1. 0 comma 0 comma 3 is nothing but 3 into del of n minus 1. I can write it as 3. If I add all the 3 of them, 1 plus 2 plus 3, then this is nothing but minus 1 comma 2 comma 3, which is the given signal x of n. So I can write it as equal to the of del of n plus 1 minus del of, minus of del of n plus 1 plus 2 into del of n, and the last one is plus 3 into del of n minus 1. So minus of del of n plus 1 plus 2 into del of n plus 3 into del of n minus 1. Now in terms of the generalized form, I can write it as equal to, what is minus 1 here? Minus 1 is nothing but x of minus 1. So I can write it as x of minus 1 into del of n plus 1. What is 2 here? X of 0 into del of n. And what is 3 here? It is nothing but x of 1. So plus x of 1 into del of n minus 1. So if I have more samples, I can add here. This side also, if I have more samples, I can add here. So generalized form of writing the x of n, any signal x of n is nothing but sigma k is equal to minus infinite to infinite x of k into del of n minus k. Now if you put the value of n is equal to 0, I mean to say the k is equal to 0, then it is nothing but x of 0 into del of n. If I put the value of k is equal to minus 1, then it is x of minus 1 into del of n plus 1. If the value of k is equal to 1, it is x of 1 into del of n minus 1. So I am just adding all of them, so it is summation. So this is how I can represent any discrete time signal in terms of a shifted impulse. Similarly, a continuous time signal can also be written as equal to integral minus infinite to infinite x of tau into del of t minus tau. Just in the place of small n, I am writing capital N. In the place of k, I am putting tau. In the place of summation, I am putting integration. Okay, so you should know about impulse response. You should also know about representation of a particular signal in terms of shifted impulse, so that you can understand the convolution very simply. Now let us start to understand the concept of convolution. These are the basics that are required for the impulse response as well as the representation of a signal in terms of an impulse. In the last lecture, we have seen about the basic system properties like linearity, time invariance, stability, causality, etc. So I advise you that first of all you watch that particular lecture, so that this particular lecture is going to be a little bit more clear to you. Now let us try to understand the concept of convolution. So let me consider a particular system which is an LTA system. Now I told you that any LTA system can be represented by its impulse response. Now tell me, if I give the input of the system as x of n, let me consider the input of the system is an impulse. Instead of considering it as x of n, let me consider it as an impulse, del of n. So for an LTA system, if I give the impulse, if I give the input as an impulse, then what is the response going to be? If the input is the impulse, then the response is going to be the impulse response. So the output is going to be h of n. When input is del of n, the output is h of n. When the input is del of n minus 1, then what is the output? Can I write it as equal to h of n minus 1? Can I write? Yes or no? Yes, I can write. Why can I write? I can write it because it's a time invariant system. And in the case of a time invariant system, we have learned that if x of t is going to give you if the x of t is going to give the output as y of t, then x of t minus tau is going to give you the output as y of t minus tau. Okay, now when we know that del of n is going to give us h of n, using the time invariance property, I can write that x of n minus 1 is going to give me h of n minus 1. Similarly, okay, I mean to say del of n minus 1 is going to give me h of n minus 1. Similarly, del of n minus 2 is going to give me h of n minus 2. Right? Let me give the other extension. Del of n plus 1 should give me h of n plus 1 using the same time invariance property. Del of n plus 2 has to give me h of n plus 2. This is also using the concept of time invariance. That is clear? That del of n gives h of n, del of n plus 1 h of n plus 1, del of n plus 2 h of n plus 2, del of n minus 1 h of n minus 1, del of n minus 2 h of n minus 2. Now what I am going to do is that, tell me one thing, if I multiply any scalar a with the del of n, what is the output going to be? Can I write the output is going to be a into h of n? Yes, because the system is linear, and in the case of a linear property, it has to satisfy the scaling. When input is x of t, the output is y of t, then a into x of t has to give me a into y of t. So that is clear. So del of n, if the output is h of n, a into del of n has to give me a into h of n. So in the place of a, I just want to take any other scalar. Let me take the scalar as x of 0. So when I multiply del of n with the del of n x of 0 is nothing but a sample of x of n at n is equal to 0. So I am just multiplying because the x of 0 is going to be a sample which is a scalar quantity. So I am writing it as x of 0 into del of n. Here also, using the linearity property, I can also multiply x of 0 at the output. Okay, this is the closed brackets. So x of 0 into h of n. X of 1 into del of n minus 1 has to give me x of 1 into h of n minus 1. X of 2 into del of n minus 2 has to give me x of 2 into h of n minus 2. X of minus 1 into del of n, I'll tell you why I'm multiplying only x of minus 1 here, only x of 0 here, I'll tell you. But we know that whenever you're multiplying any scalar, at the output also you have to multiply with the same scalar. So x of minus 1 into del of n plus 1 should give me x of minus 1 into h of n plus 1. Similarly, x of minus 2 into del of n plus 2 should give me x of 2 into h of n plus 2. Now I want to add all of them. Now tell me whether this is possible or not. Can I say that if I add all of them at the input, at the output also I should add all of them? If I add all of them at the input, at the output also I should add all of them. Is it okay or not? Why is it okay? Because once again the system is linear, and inside the system of linearity, it should also satisfy the property of additivity. Yes or no? Additivity is a part and parcel of the property of superposition, which is required to satisfy for the system to be linear. So here, if I add here, at the other end also I have to add, because the system is a linear system which has the inbuilt additivity property. So if I add all of them, this is nothing but sigma k is equal to minus infinite to infinite x of k into del of n minus k, which is nothing but your x of n. So if I add all the samples, this is nothing but x of n. Now here if I add all the samples, it is going to be equal to the of sigma k is equal to minus infinite to infinite x of k h of n minus k. Sigma k is equal to minus infinite to infinite x of k into h of n minus k. The output I can write it as equal to y of n. So I can just simply write that when I have an LTI system whose impulse response is h of n, the input is x of n, then the output y of n can be represented as equal to that of sigma k is equal to minus infinite to infinite x of k into h of n minus k. Now this is what we call as a convolution. This is the operation that we call as a convolution. This we can write it as equal to that of x of n convolved with the of h of n. We can write it as x of n convolved with the of h of n. So simply x of n convolved with h of n is the operator that we are going to have here is the required convolution operator, which relates the input, okay, the output, input and the impulse response. So whenever you know the impulse response of a particular system, whenever the impulse response of the system is known, okay, of course we know the input, so it means that we can directly know the output provided the system is going to be an LTI system. If the system is not LTI system, then we cannot use convolution. Okay, probably if you are using convolution, then the answer that you are going to get will not be equal to the of y of n. Okay, so you have to ensure that the system is going to be an LTI system. So this is how a convolution is born. Now we are not going to look into the process of a convolution, that probably we'll look into another lecture. Here we are going to look at the important properties of the convolution. Why? Because convolution is going to be a little bit more complex operator. Generally what we try to do is that we try to escape convolution using some techniques like transformation theory, Fourier series, Fourier transform, Laplace transform, Z transform. Those are the ways by which we can transform a particular time domain signal into a frequency domain, so that the convolution in the time domain is going to become a multiplication. And we know that multiplication is a very simple operator. So by multiplying that particular domain, we bring back to the time domain. So it's going to be very simple. So that is how we try to generally avoid. In examinations also, we try to avoid using the actual concept or conventional method of convolution. So there it's very important to discuss about the shortcuts that are required to solve the problems based on convolution. So in this particular lecture, we'll try to focus on the important properties that are required, okay, so that we can solve the problems which are based on convolution. So first of all, we'll look at the discrete domain. I'll just take an example. The example is that the input is given as something like the 4 sample sequence 1, 2, 3, 4, and the impulse response h of n is going to be also a 4 sample sequence 4, 3, 2, 1, and I want the response y of n provided the system is an LTI system. It is clearly given the system is an LTI system. I just want the output y of n, which is nothing but x of n convolved with the of h of n. To solve the problem, we generally don't use the direct method. Of course, we can use the direct method, but in the examination, we generally don't use the direct method. We go for the shortcut method, which is nothing but the tabular method. Tabular method is the preferred shortcut method whenever you want to convolve two finite length sequences. So here I want to write the x of n, and here I want to write the samples of h of n. So let me write the samples of x of n. The samples of x of n are nothing but 1, 2, 3, 4. The samples of h of n are 4, 3, 2, 1. So here I just want to multiply. I want to multiply the samples that I have over here. So after multiplication, 4 into 1 is going to give me 4, 4 into 2 is going to give me 8, 4 into 3 is going to give me 12, 4 into 4 is going to give me 16. 3 into 1 is 3, 3 into 2 is 6, 3 into 3 is 9, 3 into 4 is 12. 2 into 1 is 2, 2 into 2 is 4, 2 into 3 is 6, 2 into 4 is 8. 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3, 1 into 4 is 4. So after that, I just want to draw some diagonals. I just want to draw some diagonals over here. Okay, well, first thing what I have done is that I've just written x of n, the input samples over here and the impulse response samples here. Okay, then I tried to start multiplication. Okay, the table, I have a table, now I have to multiply. So 4 into 1, 4 into 2, 4 into 3, 4 into 4. 3 into 1, 3 into 2, 3 into 3, 3 into 4 and so on. After that, I am just drawing some diagonals here. I am just drawing some diagonals. And all the diagonal elements are now going to be added. I am just going to add all the diagonal elements. Now I am just going to write the elements that I have: 4, 11, 20, then 5 plus 9 plus 16 is going to be 30. And then you're going to have 20 once again. And then 11. And then 4. Okay, I'll have 4, 11, 20, 30, 20, 11. Okay, and the arrow will be here. I'll tell you why the arrow is here. Why not at the other points? So this is the tabular method by which two finite length samples can be convolved to produce the response. Now this is going to be the output y of n. Okay. Now I hope the method is very clear to you. We'll solve some more problems so that this particular method is more clear. Now what I want to see is that I just want to know some properties or shortcuts so that some problems based on the same concept can be easily solved. So what are those shortcuts? I'll tell you. So I have two inputs, I mean to say the input signal and the impulse response, and I have an output which is y of n. Now I am going to tell you some properties which are very helpful in the examination. So the properties are something like this: when x of n the input and h of n the impulse response are convolved, the response y of n has following properties. Now what are those properties? Number one, the lower limit of y of n will be equal to LL1 plus LL2. What is LL1? LL1 is the lower limit of x of n. And LL2 is going to be the lower limit of h of n, and LL is going to be the lower limit of y of n. So the lower limit, which is nothing but y of n, will be equal to the lower limit of x of n plus the lower limit of h of n. And similarly, the upper limit of the y of n will be equal to the upper limit of x of n plus the upper limit of y of n. So UL1, UL2 and UL. So UL1 is the upper limit of x of n, UL2 is going to be the upper limit of h of n, and UL is going to be the upper limit of y of n. This is the first very important property. The lower limit of the resultant is going to be sum of the lower limits of the inputs, and upper limit of the resultant is going to be the sum of the upper limits of the inputs. So what is the lower limit of x of n? Lower limit of x of n is 0. Lower limit of h of n is 0. The lower limit of y of n is also going to be starting at n is equal to 0. That is the meaning of this one. So here you are starting at 0, here you are starting at 0, here also you are going to start at 0. That is why we have an arrow here. The upper limit, what is the value? 0, 1, 2, 3. The sample value is equal to n is equal to 3. Here also the sample value is n is equal to 3. So when I add the upper limit is going to be the upper limit of the resultant is going to be the upper limits of the individual signals. So 3 plus 3 is going to be equal to 6. So here the upper limit will be equal to 6 for the resultant. 0, 1, 2, 3, 4, 5, 6. So the upper limit of the resultant is going to be the sum of the upper limits of the individual signals. So this is the first property. Second property is that the length of the sequence of the resultant, that is y of n, will be equal to the L1 plus L2 minus 1. What is L1? L1 is the length of x of n. And L2 is the length of h of n. And L is the length of y of n. L is going to be the length of y of n. So L is equal to L1 plus L2 minus 1. L is equal to L1 plus L2 minus 1. So what is the length here? 4 samples. So L1 is equal to 4. Here also the length is 4 samples. L2 is equal to 4. So L is going to be equal to the of 1, 2, 3, 4, 5, 6, 7. Which is nothing but 4 plus 4 minus 1. L is equal to that of 7, which is nothing but 4 plus 4 minus 1. This will also be satisfied. The third one now is nothing but the summation of the samples of the output y of n, and the samples can be considered from minus infinite to infinite, will be equal to the product of the samples of x of n and h of n. You can just verify it. If you see the summation of all the samples, 1 plus 2 plus 3 plus 4 is equal to 10. Similarly, here also 4 plus 3 plus 2 plus 1 is also equal to 10. So here 10 into 10 is equal to 100. It means that the summation of the samples of y of n should be equal to 100. Okay, so 4 plus 11, 15, 15 plus 20, 35, 35 plus 30, 65, 85 and plus 15, 100. So the summation of all the sample values of y of n is equal to the product of summation of the input samples. So these are the three very important properties using which we can solve many problems on convolution. Okay, so let us take some gate problems to solve based on this particular concept before going into the convolution for continuous time signals. We will see some properties also for the continuous time signals which are almost similar to the what we have learned for the discrete time signals. So these are the gate problems that I am solving here. So question 1, h of 0 is equal to 1, h of 1 is equal to minus 1, h of 2 is equal to 2, and h of n is equal to 0 for the value of n not equal to 0, 1, 2. So h of n is equal to 0, otherwise similarly x of 0 is equal to x of 2 is equal to 1 and x of n is equal to 0 for the value of n not equal to 0, 2. The question is that the number of non-zero samples. So option A 5, 2, option B 6, 2, option C 6, 1, option D 5, 3. So the given question is that h of 0 is equal to 1, h of 1 is equal to minus 1, h of 2 is equal to 2. H of n is equal to 0 for the other values of n. Okay, and x of 0 is equal to x of 2 is equal to 1, and x of n is also equal to 0 for other values of n. Now the number of non-zero samples of the output sequence y of n and the value of y of 2. We have to see how many non-zero samples are present for y of n and also the value of y of 2. You can just pause the video and try to solve based on what we have discussed in the tabular method. Okay, now the solution is going to be something like this. If I want to write h of n and x of n in terms of samples, then I can write x of n is going to be equal to the of 1, 0, 1. Okay, x of 0 is 1, x of 2 is 1, and x of n is equal to 0 for the other values. All the other samples are going to be 0. X of 1 is also going to be equal to 0. Now, h of n. Now h of n, h of 0 is equal to 1, h of 1 is going to be minus 1, h of 2 is going to be 2. Now if I have both x of n and h of n, both are going to be of same length. See, if those two are of not same length, then in that particular case we can pad zeros so that they are of same length. So now here they are of same length, so I can write my x of n here, I can write my h of n here. So x of n 1 0 1 1 minus 1 2. So it is going to be 1 0 1 minus 1 0 minus 1 2 0 2. So you draw the diagonals here. Just add all the diagonal values. So just add all the values. You'll get 1 comma minus 1 comma 3 comma minus 1 comma 2. So this is nothing but your y of t. So both the arrows are present at the initial itself, right? So 0 plus 0 is going to be equal to 0 here. So y of 0, y of 1, y of 2. So y of 2 value is equal to 3. And what is the length of the sequence? Okay, I mean to say, what are the non-zero sample values? The non-zero number of samples is going to be 1, 2, 3, 4, 5. So there are 5 non-zero values of y of n, and the value of y of 3, y of 2 is going to be equal to 3. Right? So 5 comma 3 is going to be the right answer. Okay? Number of non-zero samples of y of n is going to be equal to 5, and y of 2 value is equal to that of 3. Now let us look at the second question based on the same concept. So students, here given it is an LTI system whose h of n is what we have to find given the values of x of n and y of n. X of n is 1 comma minus 1 and the y of n is 1 0 0 0 minus 1, and we have to find the h of n. You can pause the video and try to solve this particular problem. Let us see the solution here. See here, from what we have discussed, the lower limit and upper limit of output is going to be sum of lower limits of the input. Okay, lower limit of the upper limit of the output is going to be equal to sum of upper limits of the inputs. Second property that we have seen is that length of the output sequence is equal to the sum of lengths of the input sequence minus 1. The last one is the product of sum of the input samples. That is what we have discussed as the important properties. Here also, first thing that I can use here is that the length of the output sequence. See here, the length of the output sequence is 1, 2, 3, 4, 5. So L is equal to 5, L1 is equal to 2. Then what should be the value of L2? If we know that L1 plus L2 minus 1 is nothing but your L, then L is equal to 5, which is given. L1 is something that is also given, that is 2, plus L2 minus 1. It means that the value of L2 should be equal to 4. The value of L2 should be equal to 4. What we can eliminate? We can eliminate option B and option D. And then you can check with any of the sequence. Okay. First of all, you can check with the sequence h of n, considering that, assuming that the value of h of n is going to be this one. X of n is something that you know. When you convolve both of them, if you get the same answer, it means that option A is correct. If you don't get the same answer, it means that option C is going to be the correct answer. So let us do that. So here 1 minus 1 0 0, here 1 0 0 0 minus 1. I'm sorry. Okay, so the h of n that we have selected is 1 0 0 1. Students, one more important thing is that here I'm always writing the input and here I'm always writing the h of n. So can I do the opposite? Can I write the h of n here and x of n here? Yes, it is possible because convolution is going to satisfy the commutative property. So x of n convolved with h of n is equal to that of h of n convolved with that of x of n is equal to that of y of n. So that is why I have a flexibility. Okay, it's not necessary that always you have to write x of n here and h of n here. Okay, so 1 0 0 1 is what I want to test. So here 1 minus 1 0 0, all zeros, and again 1 minus 1 0 0. So if you see here, So I'm going to get the output 1, -1, 0 and 1, -1. So the arrow is present here. Now you just check whether it is equal to y of n or not. If you see the y of n is not the same, right? So this is not equal to the top y of n. What does it mean? Option A is also wrong. Option C is the right answer. So the answer is option C. Let's look at the third problem. So students, here x of n is given as n, where the value of n is going to be between 0 and 10, and x of n is equal to 0 for the other values of n. Then in that case, if y of n is a convolution of x of n with itself, then what is the value of y of 4? Okay, you can try to pause the video and try to solve the problem. So let us look at the solution. Here the output y of n is given as the convolution of x of n with itself. Now what is x of n? X of n is equal to n for the value of n between the top of 0 to 10. So x of 0 is going to be 0, x of 1 is going to be 1, x of 2 is equal to 2, so on, x of 10 is equal to 10, x of 11 is going to be 0. So if I directly use the tabular method, I'm going to have 0, 1, 2, 3, 4, 5, so on 10 here. This side I'm going to have 0, 1, 2, 3, 4 and so on till 10. I can just do the convolution 0, 0, zeros. Here 1 into 0 is 0, 1, 2, 3, 4, 5 and so on. So 2 here, 0, 2, 4, 6, 8, 10, so on. 3, 0, 3, 6, 9, 12, 15 and so on. 4, 0, 4, 8, 12, 16, 20 and so on. Let us stop here. Let me try to draw the diagonals. This is going to give me y of 0, this is going to give me y of 1, this is going to give me y of 2, this is going to give me y of 3 and this is going to give me y of 4. This is what I require. So to have y of 4, I have to just add all the diagonal values here. So the value of y of 4 is equal to the top of 0 plus 3 plus 4 plus 3, which is equal to the top. So the value of y of 4 is equal to 10. That is the answer. So the numerical entry question, so the range is generally given as 10 to 10. Okay, so till now we have discussed about the discrete time convolution. Now we are going to discuss about the continuous time convolution. The continuous time convolution is not that different from the top what we have discussed as the discrete time convolution. So if it is an LTI system at discrete time, then the input is x of n, the impulse response is h of n, the response is y of n, which is equal to the top of x of n convolved with the top of h of n, which is equal to sigma x of k into h of n minus k, where the value of k is going to be from minus infinite to infinite. Now the only difference is that when I write a continuous time LTI system with the impulse response as h of t, the input as x of t, the output as y of t, which is equal to x of t convolved with the top of h of t, which will be equal to the top of integral minus infinite infinite x of tau into h of t minus tau data. This is your continuous time convolution. X of tau h of t minus tau with an integration. See here, summation becomes integration, x of k becomes x of tau, h of n minus k becomes h of t minus tau. There is no other difference. Now, whatever we have learned, some important properties for the discrete time signals, now we are going to do the same for the continuous time signals. Let us see whether the properties are going to be identical or not. So when two signals, or when x of t, which is the input, and h of t, which is the impulse response, are convolved, then y of t, which is equal to x of t convolved with that of h of t, has following properties. The first one is that the lower limit of the resultant is going to be sum of the lower limits of the input. Upper limit of the resultant is going to be the sum of upper limits of the inputs. Okay, so the second thing is that the duration of the resultant is going to be W1 plus W2 minus 1. What is W here? W is going to be the width of resultant, width of y of n. W1 is the width of x of n. Let us write it as x of t's and y of t's. So y of t here it is x of t. W2 is the width of h of t. So the width of the resultant signal is equal to the sum of the widths, and there will not be minus 1. Okay, in the case of a discrete time signal, we have learned it as equal to L is equal to L1 plus L2 minus 1. But here it will be a mistake if I write minus 1 also. It should be W is equal to W1 plus W2. There is no minus 1, which is a important correction that we have. And the last one is identical. There what we have seen is that the sum of the samples of the output is equal to the product of sum of the input samples. So here, instead of writing it as sum of samples, we use the integration. Integration is nothing but area. So the area or the integration of y of t is equal to the product of the integrations of the input signals. Okay, the area or the integration of the output is equal to the product of integrations of the inputs. So these are the three very important properties which we have already learned, but with some change here, and the change is generally to the second property. Let us try to solve a problem which was asked based on the properties of the convolution. Okay students, you are given the x of t, which is the input, h of t, which is the impulse response. We have to find the output, which is y of t. You can pause the video and try to solve the problem. Okay, so let us try to solve this particular problem. See here, x of t is having a width from minus 1 to the value of 1. Okay, x of t is having the width which is equal to from minus 1 to the value of. Second thing is that h of t is from 0 to 4. So what should be the lower limit of the output? Lower limit of the output is nothing but sum of the lower limits of the input. So minus 1 plus 0. Minus 1 plus 0 is going to be minus 1. So it has to start at minus 1. So what I can do is that I can just eliminate option B. Upper limit. So upper limit here is 1, upper limit here is 4. So 1 plus 4 is equal to 5. 5 should be the upper limit of the resultant signal. So here 7 is the upper limit, gone. Now we are left with two options, option C and option D. Okay, so we have used one property. Second property is that we can use the summation. Okay, the summation of the output is equal to the product of summations of the input. So what is the summation here? Here you have two impulses. One is a positive impulse, the other is negative impulse. So the addition is going to be equal to 0. Right? The summation of the input is going to be equal to 0 because here the area is 1, here the area is minus 1. 1 minus 1 is equal to 0. Now here the area of this one is nothing but it's a triangle, right? Half into base into height is going to be equal to the top. Half into base, which is 4, into height, which is equal to 1. So the area is equal to 2. So y of t should have the area which is nothing but equal to the product of the areas of the individual inputs. So 0 into 2 is going to be equal to 0. So the output should have the area is equal to 0. Now can you tell me in the option C, can we have the area is equal to 0? Everywhere it is positive value. So when you are adding, it is also going to be positive, right? So upon integration, you are going to have a non-zero value. Here, it can be a 0 value because you are having a positive and you should have a negative here. So definitely if you add it, there is a possibility of having a 0. Okay. So because there is no other option, there is only option D that could be the answer. I'm ticking marking on it. Option D is the right answer. So this is how, using the properties of these simple properties, basically we have learned 3 important properties, right? One is the lower limit, upper limit. The next one is the length or width of the resultant signal. The last one is the summation or area of the resultant signal. So using these particular properties, we were able to solve the problems. Okay. One more thing that we have learned is the tabular method. This is for today. Hope you have enjoyed and learned a few things which are important for the GATE examination, and wish you all the very best. Thank you.